In this video, we're going to talk about the joint cumulative distribution function. And I say for completeness, we are going to talk about this because, strictly speaking, one can get away with knowing just the density functions. In fact, that is more useful, I think, is to be working with the density functions rather than the cumulative distribution functions. But this is a topic that is of some use, and so we will cover the properties of it in this video. And so here is the definition. If x and y are jointly distributed, and it doesn't matter for the definition whether they are discrete or continuous, then the joint cumulative distribution function, or joint CDF, is a function f of xy such that it gives us the probability that x is less than or equal to little x and y is less than or equal to little y, remembering that the comma means and. And so that is very similar to our single variable CDF, right, where the single variable CDF of a random variable x was defined as the probability that x is less than or equal to little x. So we've just introduced a second variable here, y, but the definition is analogous. So let's look at a quick example here. This one is discrete. So let's say that x and y have joint probability mass function, p of xy, given by the following table. And let's let f of xy be their joint CDF. Find f of 2, 3. So f of 2, 3 is the probability that x is less than or equal to 2 and that y is less than or equal to 3. And so we could do that entirely from the table. We have the information there, but it is useful to look at this graphically. If we are talking here about points in the xy plane, then x is less than or equal to 2 are points that are to the left of x is equal to 2. And if we're talking about points where y is less than or equal to 3, then we're talking about points that are below y equals 3, the green line. And so we are talking about everything that is sort of to the left and below our point here. This is our point 2, 3. And some people like saying southwest of that, right? South and west, right? It's the quadrant that is below and to the left of that point. And so every one of the points in the table that fits here, and I've circled them, everything that is less than or equal to falls in the region or on the boundary. And so we have a quick way of identifying those points visually. And so here, if we're looking to find these points, well, we can just add them all up in the table. And since they start here, since they start at 1, since the points all go from 1 up to, well, in the case of x, 3, in the case of y, 4, I can express this as a nice sum. And that is actually, right, if this is little x and this is little y, this is like the sum to little x and the sum to little y, which is going to make some sort of analogy with the continuous case in just a moment. But so we've identified those points. We add them up and we get our answer. So graphically visualizing them as points, or this function as a region in the xy plane, is going to be useful. So here, let us look at the properties of the CDF, the first of the joint CDF. The first is this, right? The first is this. If we have x1 less than x1 less than x less than or equal to x2 and y1 less than y less than or equal to y2, that can be calculated using this formula, which you look at and you might think, well, that's a little bizarre. In the single variable case, right, in the single variable case, we would have had the following. We would have had f of x as the joint CDF, and if we wanted the probability, if we wanted the probability that A is less than X is less than or equal to B, we would have written that as F of B minus F of A. And that would have been straightforward in the answer. And so here you might look at this and think, well, that should just be F of the top values minus F of the bottom values. But it's not. It's not even minus the bottom values. It's plus them back in and minus these sort of cross values where you've got the small x and the higher y, and the higher x and the smaller y. So what is going on there? To see why this formula is valid, it is very useful. It is very useful here to look at this, kind of region. And so let's look at a geometric proof of this. Now, there's a lot of colors overlapping here, so I'm going to get rid of a couple of them and rebuild it for you. So let's look at this. So the first here, this probability, if we take f of x2, y2, well, first of all, actually, let's take a look here. We're looking for x between x1 and x2, and we're looking for y between y1 and y2. So the probability that we want is actually the square. There's actually this square here, which is outlined in red. Now, if I were just to take f of x2, y2, well, I get everything southwest. I get everything below and to the left of that point. So I get that entire region in green here, right? Everything that is below this line and to the left of that line. So I get the entire region. Now, I don't want that entire region. I only want the square that's in red. So I have to subtract off some stuff. If I subtract off here, if I subtract off this is to the left of x1 and below x2. So if I subtract off the bit in purple, then I am subtracting off to the left of x1 and below x2. So I'm subtracting off all of this. Right? So that's good. I've gotten rid of a lot of it, but not all of it. I also need to subtract off, well, this region, don't I? Yeah? And to subtract off that region, I need to subtract what is to the left of x2 and below y1. So if I subtract that off, well, then I've subtracted everything I need to subtract. But wait, oops. If you looked at this region here, it was subtracted off one too many times. It was included in green, subtracted in purple, and subtracted in blue. And so we're down one. And so what happens? We need to add that region back in again. And so there graphically is a visualization of why this formula makes sense. Second property, f, the CDF, the joint CDF, f of infinity equals 1. Now that is a common notation, right? But please do not think that I am actually plugging in infinity. That is a shorthand. That is a shorthand for either the maximum values in the support, if those maximum values are finite, and if they are not finite, then we are talking about the limit. So, to see why that is true, well, this is the definition of the joint CDF. And if we're taking the maximum values, or the limit as we go to infinity, well, x is always less than or equal to its maximum, y is always less than or equal to its maximum, and so that probability is 1. The next one, the marginals, f sub x of x, the marginal CDF, not PDF, the marginal CDF is this. So f sub x of x is joint CDF f of x and infinity. Again, the same thing with infinity. We're either talking about the maximum y value or the limit as y goes to infinity. The analogous definition for the marginal CDF for y, f of x as its maximum value or limit as we go to infinity, and y. And why is that true? Well, let's just look at the x case, because the analogous thing is true for the y case. Here again is the definition of the joint CDF. If y gets replaced by its maximum value, well, y is always less than its maximum value, and so that, remember this is and, that intersection adds nothing, right? That intersection restricts nothing. So we actually end up with just the probability that x is less than or equal to x, because this is always true, and that is the definition of the single variable CDF of x. So next property and last property, for continuous random variables, with joint density function f sub x. If we are looking, again, this here, if we're looking for probability in a region to the southwest, to the left of x and below little y, if this is the point xy, then using integration, that comes out to be exactly this formula. So the integral from minus infinity to little x, from minus infinity to little y of the density. And because x and y are variables here, right, those are the variables in the CDF, that's the point that we're looking for. We need to use dummy variables like in the fundamental theorem of calculus. So we use u and v here, but you could really use anything that you wanted to. And then we have here, if you want to get rid of the x and y, no, that's not what I mean. If you want to go backwards, from the CDF back down to the density, well, you've integrated in the y and integrated in the x. Well, you just take the mixed second partial, and if everything is continuous, it doesn't matter which order you do that in. You integrate, you differentiate in terms of first with respect to x first, or y, and vice versa, and you'll get back to the density given the joint CDF. So those four properties, let us go and check them in a little example here. So we have two examples, one where we're going to check the properties and one where we're going to see just sort of a more of an applied problem. So let x and y have joint density f of xy given here. So 2 over x squared y cubed for x is greater than 1 and y is greater than 1. Find the joint CDF and verify those four properties. So the joint CDF is the formula that we had exactly here. So we're going to integrate from minus infinity to x, from minus infinity to y, using two dummy variables, so f of u, v, dv, du, plugging in those values, right? Our support only starts at 1, so we're going to go from 1 to x, 1 to y. Here is our density function with the u replacing the x and the v replacing the y, dv, du. Now this is on a rectangle, right? This is 1x by 1y, so we're on a rectangle, and this factors, right? So I can use our nice little result from double integrals that I can factor the integral and do a single integral for the u from 1 to x and a single integral for the v from 1 to y, and doing those, finding the correct antiderivatives, this is what we get as the joint CDF for x and y. Now property number one was this formula, right? This zany formula where you're subtracting regions and adding them back in again. So let us use that to find the property that 2 is less than or equal, is less than x is less than or equal to 3. Actually, it doesn't matter for a continuous whether the equal sign is there or not. Obviously, that does matter for a discrete, but it doesn't matter for a continuous variable. And 1 is less than y is less than or equal to 4. So plugging that into this formula here, right, f of top values minus the two cross values, right, the small x, high y, small y, high x, and then add back in the two small values, plugging those into that formula right there, right? If you just plug this in and crunch through the numbers, you are going to get 5 over 32. Now, I say let's verify those properties, and so we can do this the same way that we would have done it a couple weeks ago, or until the start of this video even, right, we can do it by integrating. We can do it by integrating. And so we are looking here at a region from 2 to 3 and from 1 to 4, so a rectangle that kind of maybe looks like this, from 2 to 3 and from 1 to 4, and so that is the region that we want to integrate over to find the probability, and so we simply integrate, and if you calculate through, again, I'm splitting this up, we're on a rectangle, and this the function factors, so we can split up the integral as a product of integrals. You crunch through again, and you will find, lo and behold, oh marvel of marvels, that you do get the same answer. So property 1 is verified. Now, property 2 is nice and quick. It says if we go to the maximum value, well, the maximum value is infinity this time, right? We are here, our support was for greater than 1 and greater than 1 for both of those values. So I'm taking the limit here. This actually means the limit as we go to infinity. The limit as we go to infinity. And that property said that should give us 1. Well, if you take those limits, you will indeed get 1. So thank goodness, because it would be rather upsetting if I told you the property and it turned out to be false. So the marginal CDF is one of those limits. It's the limit as y goes to infinity. So we are going to do one of them because the other would be analogous. So to check that property, well, we are going to calculate this by first principles, right? So to calculate the joint CDF, well, first I know the joint PDF, and then I need to integrate it. So to calculate the marginal PDF, I need to integrate out the y. So integrate out the y, which over the support is from 1 to infinity, of the density function dy. You calculate out that integral, and you are going to get here as your marginal PDF. To get the marginal CDF, I need to integrate the PDF. And I need to do that, well, if we are a little fast and loose here, we're going to integrate. We're not going to worry about where it's 0. We're just going to integrate the non-zero part. So we're going from 1 to x, and this is obviously when x is greater than 1. And if we integrate, we again need a dummy variable of the density function. Integrate that, and you get this as your joint your marginal CDF, and the property says if we take the limit here as y goes to infinity of our density function, right, our joint, I should really think before I speak, of our joint cumulative distribution function, then we should get the same answer. And so if we take the limit as y goes to infinity, right, y goes to infinity right here, we do indeed get the same answer as we did through first principle integration. And lastly, property 4 says if we take the second mixed partial of the joint CDF, then we should get back the density function. So let's just do that. Right, remember the mixed second partial is, if I split it up, it is like this. I take the derivative with respect to y first, and then the derivative with respect to x in the order that it's written here. Again, it doesn't really matter if everything is continuous. So if you're taking the derivative with respect to y, I've rewritten the joint CDF in terms of negative powers to make the differentiation easier. So x is a constant. We differentiate in terms of y, so we get minus the minus 2, so positive 2, subtract 1 in the power. Now we differentiate with respect to x. The y is a constant, so here is the derivative with respect to x. The minus 1 minus minus gives us a plus, subtract the power, and then put those back into sort of more pleasing form notation, and we get the exact same density that we had before. So the properties, in fact, are all verified. Now, lastly, example 2, what would an applied kind of problem look like, or what could an applied problem look like? Well, let's see. So let x, y have joint CDF given here. So x squared y plus xy squared minus y cubed on this support. Find the expected value of y. Now, that's going to involve a couple steps because this is a joint CDF. To find the expected value of y, I need to integrate a PDF. And so what are we going to do? Well, we're going to use one of the properties. One of the properties is that if I take, right, x at its maximum value, which is notated by infinity, but might not actually be infinity. In this case, the maximum value is 1. So if we put in 1 for x and y, we are going to get the marginal CDF of y. So we plug in 1 to this formula, you get this. Now that is a CDF. That is not what you need to find the expected value. You need the PDF. And so how do you find that? The marginal PDF of y is the derivative of its CDF, right? We've used that a couple times throughout the course, and so if you take the derivative of the marginal CDF, you get this. Now you've got the PDF for y, and if you want the expected value of y, well, now you can use the expected value formula with the PDF. You can integrate over the entire support of y times the density of y dy, and so we plug that in. The support for y is from 0 to 1. Y goes here, y times the density of y, right? And that density function is just from up there. You expand and crunch through that, and you will get the expected value here as 5/12. So a couple of properties using, right, a property of the joint CDF, a property that we have used in the past, the relationship between the density and the cumulative function, and the definition of expected value. So not a difficult problem, but a nice one in that it puts together little elements from all throughout the course.